In this lecture video, we're going to learn all about binomial probability distributions. A probability distribution is considered a binomial probability distribution if it meets the following requirements. First, the procedure must have a fixed number of trials. It cannot go on indefinitely. The trials must also be independent. That is, the probability of one trial is not affected by the outcome of another. Third, each trial must have all outcomes classified into only two categories. We often refer to these as success and failure. And finally, the probability of a success must remain the same in all trials. If we meet all of these requirements, we do in fact have a binomial probability distribution, and we can treat it a little differently. For example, let's look at this procedure and see if it results in a binomial distribution. The procedure is tossing a coin 10 times and keeping track of the number of tails that occur. First, does this procedure have a fixed number of trials? Yes, we are told that we are tossing the coin 10 times. Second, are the trials independent? Yes, what the coin lands on in one trial does not affect what the coin lands on in a next trial. Third, are all outcomes classified into exactly two categories? Yes, there are only two options, tails or not tails, a success or failure. Finally, does the probability of a success remain the same in every single trial? Yes. For each coin flip, the probability of a success is 0.5. Since we meet all four of these requirements, this is a binomial distribution. Now consider the procedure of rolling a die until the number 2 appears. Does this procedure have a fixed number of trials? No. There is not a fixed number of times that we are rolling the die. We're going to roll the die until a 2 appears. So we might be rolling the die 2 times or 150 times. There's not a fixed number of trials, so we do not meet the first requirement, and this is not a binomial distribution. In order to calculate the probability for each value of x, we have the following formula. In this formula, n refers to the number of trials. X is the number of successes in n trials. P refers to the probability of a success in one trial. And Q is the probability of a failure in one trial. Because of this relationship between P and Q, it must be that Q is equal to 1 minus P. And finally, when we calculate P of x, we're talking about the probability of exactly x successes in n trials. Let's try out this formula with an example. The probability of getting a jackpot on a particular slot machine is 1 over 2,000. Let's find the probability of getting exactly 2 jackpots in 5 trials. First, let's list out the variables that we have. N is the number of trials, and we are going to play this game 5 times, so N equals 5. X is the number of successes that we're interested in, and since we're finding the probability of 2 jackpots in 5 trials, X is equal to 2. The probability of winning in this case, or P, is equal to 1 over 2,000. And the probability of a failure in this case, that is not getting a jackpot, is everything else, or 1,999 over 2,000. Now we have everything we need to calculate the probability of exactly x successes in n trials. The formula is n factorial divided by n minus x factorial times x factorial times p raised to the exponent of x times q raised to the exponent of n minus x. Substituting our values for n, x, p, and q, we have n factorial, or 5 factorial, divided by n minus x, or 5 minus 2 factorial, times x factorial, or 2 factorial, multiplied by p, 1 over 2,000, squared, times q, 1,999 over 2,000, raised to the exponent of n minus x, or 5 minus 2. You can put this directly into your calculator, just make sure that you use really good order of operations. When we put this into our calculator, we get 2.49625 times 10 to the exponent of -6. In other words, the probability of getting 2 jackpots in 5 trials is approximately equal to 0.000025. What if instead we wanted to find the probability of getting less than 2 jackpots in 5 trials? In order to calculate the probability of x being less than 2, we need the probability of getting no jackpots in 5 trials plus the probability of getting 1 jackpot in 5 trials. I'll leave the details out so that you have a chance to practice. But when you walk through these steps, the probability of getting no jackpots in 5 trials is 0.9975. And the probability of getting exactly 1 jackpot in 5 trials is 0.0025. Notice that when we add these together, we get 1. Of course, there was some rounding involved in these numbers, but we basically found that there's a 100% chance of getting less than 2 jackpots in 5 trials. Now, in order to find the probability of getting at least 2 jackpots in 5 trials, we need to take into consideration the option of getting 2 jackpots, 3 jackpots, 4 jackpots, and 5 jackpots in 5 trials. Or we can recognize that the probability of x being greater than or equal to 2 is equal to 1 minus the probability of x being less than 2. And we already found that probability in part B. Again, I'll leave these details to you to practice. Now that binomial probability formula can be a pain. For this example, let's try doing the calculations with our calculator. In this example, we are told that McDonald's has name brand recognition of 95% around the world. That means that if we randomly select any person from the entire world, the probability of them recognizing the McDonald's brand is 0.95. Let's find the probability that 3 out of 5 people chosen would recognize McDonald's. In this situation, our n is equal to 5 because we're looking at 5 people and wondering how many will recognize McDonald's. Specifically, we're looking for the probability that 3 out of 5 will recognize McDonald's. That's asking for 3 successes out of 5 trials. Our value for p, that's the probability of success, is 0.95. And Q, the probability of failure, is everything else, 0.05. In order to calculate this using our calculator, we're going to use the function binom PDF, which takes as its input values n, p, and x. So in our example, we're going to find p of 3, and that's going to be equal to binom PDF of 5.953. Binom PDF can be found in the DISTR menu, which we can get to by clicking Second and VARs. We can then scroll down and find Binom PDF as option A. If you're using a TI-84, this menu will pop up for you to enter the number of trials, your p-value, and x-value. From there, you can highlight the Paste button and click Enter. If you have a different TI calculator, when you select Binom PDF, your screen might look like this. And you'll simply enter the values of 5.95 and 3 in that order, separated by commas. Once you click Enter, you'll be given the probability of exactly 3 successes in 5 trials. So the probability of exactly 3 out of 5 randomly selected people recognizing McDonald's is 0.02143. If 95% of people around the world recognize McDonald's, why is this number so low? We are finding the probability that exactly 3 out of those 5 people recognize McDonald's, not at least 3. In other words, we also found the probability that when randomly selecting 5 people, 2 of them will not recognize McDonald's. That's why the probability is so low. To find all of the probabilities for all values of x, we can simply leave off the x value. By not specifying a number of successes, Binom PDF will list out for us all of the probabilities for each x value. And by scrolling to the right, you can see all 6 options, 0 through 5, listed in order. From this menu, that would mean we would enter 5 trials, 0.95 for p, and leave the x value blank. In effect, this created a binomial probability distribution for us in one step. Now that we have a basic understanding of a binomial distribution, let's talk about calculating the mean, variance, and standard deviation. The good news about a binomial distribution is that calculating these parameters is easier than calculating them for a typical probability distribution. For a given situation, if we know n, p, and q, the mean is simply the product of n and p. The variance is the product of n, p, and q, and the standard deviation is the square root of the variance, or the square root of the product of n, p, and q. Let's try these out with an example. The final exam in a course consists of 100 multiple choice questions. Each question has 5 possible answers, and only one of them is correct. An unprepared student makes random guesses for all of the answers. First, let's find the mean and standard deviation for a student like this that's randomly guessing throughout the entire exam. To do that, we'll need our n, p, and q. N is the number of trials. In this case, there's 100 questions, so n is equal to 100. And the probability of getting any one of those questions correct is 1 divided by 5, or 0.20. And Q is the probability of getting a question incorrect. And with 5 options, 4 of them are incorrect, so Q is equal to 4 divided by 5. Now we can calculate the mean, which is simply the product of n and p. N times p in this case is 100 times 1 over 5, or 20. The variance in this case, sigma squared, is equal to n times p times q, or 100 times 1 over 5 times 4 over 5. That's equal to 16. And the standard deviation is, of course, the square root of the variance, or the square root of 16, or 4. Now that we have the mean and the standard deviation, we can determine if it would be unusual for a student who is guessing on every question to get 60 correct answers. In order to answer this question, let's first find out what would be considered usual and see if 60 is outside of those bounds. With our mean of 20 and our standard deviation of 4, 2 standard deviations below the mean, or mu minus 2 sigma, would be 20 minus 2 times 4, or 20 minus 8, or 12. 2 standard deviations above the mean, or mu plus 2 times sigma, is equal to 20 plus 2 times 4, or 20 plus 8, or 28. That means that usual values in this case are between 12 and 28. In other words, 60 is considered unusually high. It is much more than 2 standard deviations above the mean. That concludes this lecture video on binomial probability distributions.